Right now, a spacecraft that was launched before you were born is racing through the darkness. It's traveling 25 billion miles from Earth, farther than any human creation has ever gone. But here's something that will amaze you. It would take this space probe 73,000 years to reach our nearest star. We're going to explore beyond the edge of everything we know. We'll look at ships that use nuclear explosions for power, meet imaginary civilizations that harvest energy from entire stars, and discover why the universe itself might have an end date. What we're about to learn will change how you see our place in space. Picture yourself standing at the shore of an ocean that stretches beyond every horizon you can imagine. You might think our solar system ends at Pluto, but that's not true. Way beyond that distant, icy planet, there's a region called the heliopause. This is where our sun's influence finally stops working. This invisible border sits about 11 billion miles from home, so far that light from the sun takes 16 hours just to reach it. If you drove a hour at highway speed without ever stopping, the trip would take you 12 million years. Think of our solar system like a giant soap bubble floating in space. The sun creates this bubble by blowing something called solar wind, a stream of tiny charged particles racing outward at over 1 million miles per hour. For billions of miles, this wind pushes against the emptiness of space, creating a protective shield around everything we know. But eventually, even the sun's mighty breath grows weak. At the heliopause, our solar bubble meets the fierce winds from other stars in space. Here, alien particles from distant stars crash into our cosmic neighborhood like waves against a seawall. The temperature drops to nearly absolute zero, the coldest temperature possible. Even the atoms that make up space itself change. You've left the influence of the only star humanity has ever known. Voyager 1 spacecraft crossed this boundary in 2012, becoming the first human-made object to enter true interstellar space, the space between stars. Its radio signals now take over 21 hours to reach Earth, which is longer than an entire day. The probe sends back messages from a place so foreign that our best scientists are still trying to understand what it all means. But here's what should really make your head spin. This edge that took us 35 years to reach with our fastest spacecraft represents less than 1/10,000th of the distance to our nearest neighbor star. Or, imagine taking a single step on a journey that would circle the Earth 2.5 million times. That's how far we've come, compared to how far we still need to go. The heliopause isn't just a border, it's a warning. Beyond this point, the rules change completely. The gentle warmth of our sun becomes meaningless. The magnetic fields that protect us from deadly radiation disappear. Even time itself behaves differently when you're moving between the stars, at impossible speeds. Standing at this cosmic shore, you realize that leaving our solar system isn't just about building faster rockets or better technology. It's about becoming something entirely new, a species capable of surviving in the vast, cold darkness between worlds. Two golden records spin through space, carrying the sounds of Earth to civilizations we may never meet. Launched in 1977, Voyager 1 and 2 were supposed to explore Jupiter and Saturn, then quietly fade into space. Instead, they became humanity's first messengers to the stars. racing toward distant suns, with messages from a blue world they'll never see again. Each probe carries a golden record containing the sounds of whales singing, babies crying, and music from every corner of Earth, like a cosmic message in a bottle. Voyager 1 travels at 38,000 miles per hour, faster than any spacecraft in history. At this speed, you could fly from New York to Los Angeles in just 4 minutes. Yet after 46 years of flying, it has barely begun its journey to the stars. The probe won't come close to another star for 40,000 years. Think of these spacecraft like ships from long ago, setting sail for unknown continents. Their captains knew they might never return, but they carried the hopes and dreams of everyone they left behind. The Voyager's computers have less processing power than your phone, yet they continue to work in conditions that would destroy any earthly molecule in seconds. The cold out there doesn't just freeze things. It changes the very atoms that make up the spacecraft. Metal becomes as brittle as glass. Electronics that worked perfectly for decades begin to fail in ways engineers never predicted. The probes are slowly dying. Their nuclear hearts grow weaker with each passing year. But these dying messengers have already revolutionized our understanding of what lies beyond. They've detected magnetic fields twisted into impossible shapes by stellar winds. They've measured cosmic rays from galaxy-destroying explosions that happened before Earth even existed. Most shocking of all, they've discovered that the space between stars isn't empty. It's filled with a thin soup of hydrogen atoms and mysterious particles from the birth of the universe. Every day, Voyager's radio signals grow weaker. By 2025, the probes will fall silent forever. Their nuclear power finally used up. They'll become ghost ships sailing through an ocean of stars, carrying our golden records to destinations we can only dream about. Scientists think that in about 300 million years, long after humans have either evolved into something unrecognizable or disappeared entirely, one of these records might be found by an alien civilization. They'll hear our music, our languages, our laughter. They'll learn that once, on a small blue planet, there lived a species crazy enough to throw bottles into the cosmic ocean. Between here and our nearest neighbor lies a darkness so complete it makes the deepest ocean trench look bright as day. Space isn't just empty, it's aggressively, violently empty in ways that human minds struggle to understand. If you made our solar system small enough that Earth was the size of a marble, the nearest star would sit 400 miles away. That's like placing a marble in New York and trying to hit another marble in Denver with a perfect throw. But the emptiness goes deeper than just distance. In the best vacuum chambers on Earth, scientists can remove almost a the air, leaving about 10 million particles per cubic inch. In interstellar space, there's less than 1 atom per cubic inch. You could compress all the matter between stars into a volume smaller than a grain of sand. Think of it like this. Imagine trying to swim across an ocean where the water is so thin you can't even feel it, so cold it would freeze your blood in seconds, and so filled with invisible radiation that it would damage your DNA from the inside out. That's what spacecraft face in the void between stars. This emptiness plays tricks with physics itself. Without air to carry sound, the universe becomes permanently silent. Without matter to conduct heat, temperatures hover just above absolute zero, negative 450 degrees Fahrenheit. At these temperatures, even helium becomes solid. Metal shatters like glass. Electronics die for reasons scientists are still trying to understand. The radiation out there makes the Chernobyl nuclear disaster look like a health spa. Cosmic rays, particles sped up by dying stars and black holes, slam into anything in their path at nearly the speed of light. A single cosmic ray carries more energy than a baseball thrown at 60 miles per hour, but concentrated into a space smaller than an atom. These invisible bullets would damage human DNA, causing cancer, brain damage, and death within months. Even worse, the magnetic field that protects us on Earth disappears completely in interstellar space. Solar wind from distant stars creates electromagnetic storms that could destroy any electronics we send out there. Imagine trying to use your phone during a lightning storm that lasts for centuries. But perhaps the most unsettling discovery is that this emptiness isn't the same everywhere. Space between stars contains clouds of hydrogen gas, cosmic dust, and mysterious dark matter that we can detect but not understand. These clouds can stretch for hundreds of light years, creating invisible walls that could damage or destroy anything moving through them at high speed. Flying through interstellar space at the speeds we'd need to reach other stars would be like driving through a sandstorm at 200 million miles per hour. Every speck of dust becomes a bullet. Every gas cloud becomes a wall of destruction. 4.25 light years away burns a star so dim you need a telescope just to see it. Yet it holds the key to humanity's survival. Proxima Centauri is our nearest neighbor star, a red dwarf star barely 1/8 the size of our sun. If our sun is a roaring bonfire, Proxima is a dying candle flickering in the cosmic wind. This tiny star produces so little light that its potentially livable planet receives only % of the energy Earth gets. But here's what should excite you. That planet, called Proxima b, sits in the Goldilocks zone, the perfect distance where liquid water can exist. It's just 4.25 light years away, practically next door in cosmic terms. At the speed of our fastest spacecraft, the journey would take only 73,000 years. Think of Proxima Centauri like a lighthouse on a distant shore. You can see its beacon and know exactly where it is. But the ocean between you and safety is filled with storms that could destroy any ship you build. The star itself weighs only 12% as much as our sun, yet it unleashes solar flares that make our worst space weather look gentle. These stellar tantrums release more energy in minutes than humanity has produced in all of recorded history. The flares bombard Proxima b with radiation levels that would sterilize the surface and strip away any atmosphere. If life exists there, it would need to hide deep underground or develop protection that makes our best technology look like paper armor. Red dwarf stars like Proxima live for trillions of years, hundreds of times longer than our sun will survive. While our solar system dies in 5 billion years, Proxima Centauri will still be burning. When the universe itself grows cold and dark, it's the ultimate long-term destination for a species planning to outlive the death of stars. But the journey to reach it represents the greatest challenge humans have ever faced. Moving at 10% the speed of light, faster than anything we've ever built, would still take 43 years, an entire human lifetime, would be spent crossing the void between worlds. Babies born on the ship would grow old and die without ever seeing their destination. The energy required to reach such speeds is almost unimaginable. You'd need to convert matter directly into energy using Einstein's famous equation E=mc. The fuel alone would weigh more than entire mountains. Yet scientists have already found dozens of potentially livable planets around red dwarf stars within 50 light years of Earth. These ancient suns offer humanity something our own star cannot: time. Billions of years to evolve, explore, and spread across the galaxy before the last stars burn out. Proxima Centauri isn't just our nearest neighbor, it's our cosmic life insurance policy. But reaching it requires us to break the most fundamental speed limit in the universe. And that's where Einstein's rules turn everything upside down. Nothing with mass can ever reach the speed of light, and that one fact might doom humanity to die on a single world. Einstein discovered that as you approach light speed, something impossible happens. Your mass increases toward infinity. To push even a single atom to light speed would require all the energy in the universe. It's not just difficult, it's mathematically impossible, written into the very fabric of reality, like a cosmic speed limit enforced by the laws of physics themselves. Light travels at 671 million miles per hour. At this speed, you could circle Earth 7.5 times in 1 second. You could reach the moon in 1 1/3 seconds. You could cross our entire solar system in 11 hours. Yet even at this incredible speed, reaching Proxima Centauri would take 4.25 years. Think of the speed of light like the ultimate highway speed limit. Except the penalty for trying to break it isn't a ticket. It's the complete destruction of physics as we know it. As spacecraft approach light speed, time itself begins to slow down compared to the rest of the universe. At 99 light speed, 1 year on your ship equals 7 years on Earth. This creates what scientists call the Bose time dilation paradox. A crew traveling to Proxima Centauri at near light speed might experience only a few months of flight time, while everyone they left behind ages decades. They'd return to find their friends and family dead, their civilization transformed beyond recognition. They'd become time travelers, trapped in a future they never chose. But the energy requirements make even this scenario impossible with current technology. To speed up a spacecraft weighing as much as the space shuttle to just 10%. 10% of light speed would require the energy output of the entire United States for over 100 years. Getting to 90-bit light speed would demand more energy than our sun produces in a century. Even if we solved the energy problem, the effects of moving at nearly light speed turn space dust into cosmic bullets. At near light speeds, a grain of sand hits with the force of a nuclear weapon. The thin gas between stars becomes a wall of radiation that would vaporize any known material. The universe itself becomes hostile to high-speed travel. Yet Einstein's equations also revealed something extraordinary. While nothing can travel faster than light through space, space itself can expand faster than light. The universe has been doing exactly this since the Big Bang. During cosmic inflation, regions of space separated faster than light could travel between them. This loophole in Einstein's laws opens a door to something that sounds like pure science fiction. We might not need to travel faster than light if we can convince space itself to move us. Instead of pushing through the cosmic speed limit, We could ride the expansion of space-time itself, but using this power requires technology so advanced it might as well be magic. Our first attempt to beat Einstein uses the most violent force in the universe. Imagine riding a surfboard on a wave of nuclear explosions, each blast powerful enough to level a city. Project Orion, conceived in the 1950s, proposed the most daring spacecraft design in human history. A ship pushed forward by exploding atomic bombs behind a massive steel plate. Every few seconds, another nuclear weapon would explode, pushing the craft forward with forces that would crush ordinary materials to powder. The physics actually work. Nuclear explosions release more energy per pound than any other known reaction. A single atomic bomb contains enough energy to power New York City for 2 weeks. Chain together thousands of these explosions, and you could speed up a massive spacecraft to 5% of light speed, fast enough to reach Proxima Centauri in less than 100 years. Think of it like the ultimate motorcycle, except instead of burning gasoline, you're exploding hydrogen bombs every 3 seconds and riding the shockwave. The spacecraft would need shock absorbers the size of buildings and a pusher plate made from materials that could survive repeated nuclear blasts. Engineers calculated that such a ship could weigh thousands of tons, yet still achieve speeds no chemical rocket could dream of. The original Orion design called for a crew compartment protected by layers of lead shielding. Astronauts would experience brief moments of crushing acceleration, followed by periods of weightlessness as the ship coasted between explosions. It would feel like riding inside a giant hammer being struck by the fist of an angry god. But the radiation exposure would be deadly. Each nuclear pulse would flood the spacecraft with gamma rays, neutrons, and radioactive particles. Even with heavy shielding, crew members would absorb doses of radiation that cause cancer, sterility, and death. The ship itself would become so radioactive that approaching it without protection would be suicide. Modern versions of pulse propulsion use fusion instead of fission, creating cleaner explosions with less radioactive waste. Fusion bombs fuse hydrogen atoms together, releasing energy directly from Einstein's equation, while producing mostly harmless helium as waste. These thermonuclear pulses could push spacecraft to 10% of light speed, while reducing radiation exposure to survivable levels. The engineering challenges remain staggering. The pusher plate would need to withstand temperatures of millions of degrees and pressures greater than the center of Earth. The shock absorbers would compress and expand like cosmic springs, each one larger than a skyscraper. The fuel storage alone would require a magazine capable of safely holding thousands of nuclear weapons. Yet computer simulations show that nuclear pulse propulsion could work with technology we understand today. Unlike exotic physics or theoretical particle, this concept requires only engineering solutions to known problems. We could build an Orion-style spacecraft within 50 years if we committed the resources. The real obstacle isn't technical, it's political. Building a spacecraft powered by nuclear weapons would require international cooperation on a scale never before achieved. The ship would essentially be a flying nuclear arsenal capable of destroying entire planets. But if we're serious about reaching the stars, we might need to ride the Tiger. Across the vacuum of space flows an invisible river of pure energy, and we're finally learning how to sail it. Light itself has momentum. Every photon that hits a surface transfers a tiny push, like cosmic raindrops striking a window. This force is incredibly weak. The pressure of sunlight on Earth equals the weight of a paperclip spread across an area the size of a football field. But in the frictionless void of space, even this gentle touch can speed up spacecraft to incredible velocities. Solar sails work like sailboats in reverse. Instead of catching wind to push through the water, they catch starlight to push through space. The sail itself must be impossibly thin, thinner than soap bubbles, lighter than butterfly wings, yet strong enough to survive the journey between worlds. Think of it like wrapping a spacecraft in aluminum foil, so delicate you could tear it with your breath. Japan's Icarus probe proved that solar sailing works in practice. Launched in 2010, this experimental craft unfolded a sail the size of a basketball court and successfully navigated through space using only photon pressure. The sail was just 7.5 thousandths of an inch thick, so thin that 14,000 sheets stacked together would equal the thickness of a human hair. But here's where solar sails become truly exciting. They never run out of fuel. Chemical rockets burn through their fuel in minutes, then coast. Nuclear rockets require massive amounts of radioactive material. Solar sails speed up continuously as long as starlight hits them, building up speed over months and years until they're moving faster than any rocket ever built. The Breakthrough Starshot project plans to use this principle to reach Proxima Centauri within 20 years. Instead of sailing on sunlight alone, they want to push tiny spacecraft with the most powerful lasers ever built. A ground-based laser array generating 100 billion watts would focus its beam on sails the size of postage stamps, speeding them up to 20% of light speed in just 2 minutes. These star chips would weigh less than a paperclip, yet carry cameras, computers, and communication equipment. Racing across interstellar space at 134 million miles per hour, they could photograph the planets around Proxima Centauri and beam the images back to Earth. The journey that would take Voyager 40,000 years could be completed in just 20. But scaling up solar sails for human crews creates problems that push the boundaries of engineering. A sail large enough to carry people would need to be hundreds of miles across, larger than most countries. Keeping such a huge structure intact while speeding up at high velocities would be like trying to preserve a spider web in a hurricane. The sails would also need to survive bombardment by cosmic dust, radiation, and the intense laser light pushing them forward. At the temperatures generated by such powerful beams, most materials would vaporize instantly. Engineers are experimenting with metamaterials, artificially structured substances with properties that don't exist in nature. Solar sails offer humanity something no other propulsion system can: the ability to ride the fundamental forces of the universe itself. We're not fighting against physics, we're learning to dance with it. Picture a spacecraft that feeds like a cosmic whale, scooping up hydrogen atoms from the void and converting them into the hottest fire in the universe. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, represents one of the most elegant solutions to interstellar travel ever conceived. Instead of carrying fuel, the spacecraft would collect hydrogen atoms from space itself using a magnetic field, stretching thousands of miles across. These atoms would then be compressed and fused together, releasing energy to power the ship forward. Space isn't truly empty. Even in the vast darkness between stars, there's roughly 1 hydrogen atom per cubic inch. That seems like almost nothing, but at high speeds, these atoms add up quickly. A ramjet traveling at 10% of light speed would sweep up billions of atoms every second, providing a continuous supply of fusion fuel. Think of it like a cosmic jet engine that breathes space instead of air. Jet engines work by compressing air, mixing it with fuel, and igniting the mixture to create thrust. A fusion ramjet would compress hydrogen from space, fuse it into helium, and use the released energy to go even faster. The faster it goes, the more fuel it collects, creating a feedback loop that could theoretically reach significant fractions of light speed. The magnetic field required would be enormous, larger than Earth itself. This invisible net would need to be strong enough to capture individual atoms while moving at nearly light speed, yet precise enough to funnel them into the fusion reactor without losing efficiency. Engineers compare it to trying to catch raindrops with a net while riding a motorcycle at 200 miles per hour. The fusion reactor itself would operate at temperatures of 100 million degrees, 6 times hotter than the core of the sun. At these temperatures, hydrogen nuclei overcome their natural repulsion and fuse together, converting a small amount of mass directly into energy according to Einstein's equation. The reaction produces no radioactive waste, only helium and pure energy. But the ramjet faces a cruel problem. It needs to be moving very fast before it can collect enough fuel to work efficiently. Getting up to that initial speed requires conventional rockets or other propulsion systems. It's like needing to push start a car that can only run at highway speeds. Computer simulations reveal another problem. As the ramjet approaches higher speeds, the hydrogen atoms it collects begin to act like radiation rather than fuel. At 20% of light speed, the fuel becomes so energetic that it actually slows the spacecraft down instead of speeding it up. The ramjet hits a wall built from the very atoms it's trying to consume. Recent designs attempt to solve this by using the magnetic field, not just to collect fuel, but to compress space itself around the spacecraft. This creates a region of higher hydrogen density while reducing the effects that turn fuel into radiation. The ship would essentially surf through space inside its own magnetic bubble. If we could build a working fusion ramjet, it would represent the ultimate expression of living off the land in space. The spacecraft would become a self-sustaining ecosystem, feeding on the universe itself while carrying human consciousness to distant stars. What if we never moved at all, but convinced the universe to bring our destination to us? Mexican physicist Miguel Alcubierre discovered something extraordinary in Einstein's equations. While nothing can travel faster than light through space, there's no limit on how fast space itself can move. His solution sounds like magic. Compress space in front of your spacecraft while expanding it behind you, creating a wave that carries you faster than light without actually speeding up. Think of it like standing on a moving walkway at the airport. You're not walking any faster than normal, but the walkway itself carries you forward at high speed. An Alcubierre drive would create a similar effect with space-time itself, forming a bubble where the ship never actually exceeds light speed relative to local space. Inside this warp bubble, you'd experience no crushing forces, no time dilation, and no deadly radiation from high-speed travel. The journey to Proxima Centauri could take days instead of decades. You could travel to the far side of the galaxy, and return home to find that only years had passed on Earth instead of thousands of years. The mathematics worked perfectly. Einstein's field equations allow for regions of space that contract and expand at any speed, even faster than light. During the universe's first moments, cosmic inflation stretched space faster than light could travel across it. The Alcubierre drive would simply recreate this process on a smaller scale. But the energy requirements make nuclear weapons look like birthday candles. To warp space around a spacecraft, the size of the Starship Enterprise would require negative energy equivalent to the mass energy of Jupiter. That's more energy than our Sun will produce in its entire 10 billion year lifetime, focused into a field smaller than a solar system. The drive also requires exotic matter with negative energy density, a substance that may not exist in our universe. This theoretical material would need to have less energy than completely empty space, creating a kind of anti-gravity effect that repels normal matter. We've never detected such material naturally, and creating it artificially might violate fundamental laws of physics. Even if we solved the energy problem, an Alcubierre drive could destroy everything at its destination. The space compression effect would accumulate high-energy particles and radiation during the journey. When the drive shuts off, this concentrated death would blast forward at near light speed, sterilizing entire star systems. Recent research suggests that microscopic warp bubbles might be detectable in our current particle accelerators. Scientists are looking for tiny distortions in space-time that could prove the Alcubierre effect exists in nature. If found, these discoveries could lead to entirely new physics and propulsion technologies. Some theorists propose that an advanced civilization could build a network of Alcubierre highways connecting star systems across the galaxy. Ships would jump from one warp bubble to another like cosmic subway stations, crossing thousands of light years in the time it takes to read this sentence. The Alcubierre drive represents the ultimate destination for human technology, the ability to step outside the normal rules of physics and reshape reality itself. But until we discover exotic matter or new laws of physics, it remains a beautiful mathematical dream. Imagine a city that sails between stars, carrying thousands of people who will live and die in the darkness without ever seeing their destination. Generation ships represent humanity's most realistic path to the stars, using technology we could build today. These massive vessels would house entire civilizations during journeys lasting centuries or millennia. The original passengers would have children, grandchildren, and great-grandchildren who grow up knowing they'll spend their entire lives aboard a ship traveling to a world they'll never reach. Think of it like the Mayflower, except the voyage takes 100 years, and the passengers' descendants won't remember why they're traveling. Gee, the ship would need to be completely self-sufficient, recycling air, water, and waste with perfect efficiency. Every atom would be precious. Every system would need to be designed to last longer than entire human civilizations. The scale is staggering. A generation ship carrying 100,000 people would need to be dozens of miles long and several miles wide. It would require nuclear reactors, farms, factories, schools, hospitals, and everything else needed to sustain human civilization. The ship would essentially be a hollow asteroid, converted into a traveling world. The psychological challenges might be even harder than the engineering ones. How do you motivate people to maintain a mission their great-great-grandchildren will complete? What happens when generations born in space decide they don't want to continue the journey? History shows that isolated populations often develop their own cultures, languages, and beliefs that differ dramatically from their origins. Computer models suggest that a minimum viable population for a generation ship would be around 10,000 people to maintain genetic diversity and prevent inbreeding. But social scientists argue that the cultural diversity required for a stable society might demand populations of 50,000 or more. These flying cities would carry more people than most towns on Earth. The ship's social structure would need to last longer than any government in human history. The Roman Empire lasted 1,000 years. The Egyptian dynasties persisted for 3,000. A generation ship to Proxima Centauri might need to maintain social unity for over 100,000 years. If launched with current technology, some designs propose using rotating sections to create artificial gravity through centrifugal force. The outer rings would spin fast enough to simulate Earth's gravity, while the central hub remains in zero gravity for manufacturing and agriculture. Diving on such a ship would be like inhabiting a giant spinning wheel, flying through the cosmic void. The ship would need to carry libraries containing all of human knowledge, genetic samples from Earth's biosphere, and manufacturing equipment capable of building anything the passengers might need. It would be humanity's backup drive flying through space, our insurance policy against extinction. Imagine closing your eyes on Earth and opening them orbiting an alien sun while your body remains perfectly preserved in a sleep deeper than death. Cryogenic preservation, or cryosleep, offers a tempting solution to the time problem of interstellar travel. Instead of living through centuries of flight time, passengers would be frozen at temperatures close to absolute zero. Their biological processes would slow to nearly nothing. They would age only days during journeys lasting decades, awakening young and healthy at their destination. The science isn't complete fiction. We can already freeze simple organisms like tardigrades, tiny water animals that look like microscopic bears, and revive them years later with no apparent damage. Some mammals can survive hours in a frozen state before being successfully brought back to life. Human organs for transplant are routinely preserved in cold storage, staying viable for hours or days. Think of cryosleep like hibernation, taken to its absolute extreme. Bears slow their metabolism during winter, surviving months without food or water. Cryogenic freezing would slow human metabolism by a factor of millions, essentially pausing life itself until reactivation. Heart rate, brain activity, and cellular processes would reduce to levels barely detectable by our most sensitive instruments. But freezing humans presents challenges that make rocket science look simple. Ice crystals forming in cells destroy their internal structure like microscopic daggers. Blood vessels burst. Proteins unfold and lose their function. The delicate chemistry of consciousness gets scrambled beyond repair. Modern cryonics companies try to solve this by replacing blood with antifreeze compounds called cryoprotectants. These chemicals prevent ice formation while allowing tissue to be cooled to temperatures where all biological activity stops. The process is called vitrification, turning the body into a biological glass that preserves cellular structure without the damage caused by freezing. Even if we perfect the preservation process, revival presents equally daunting problems. Warming the body must happen at precisely the right rate to prevent cellular damage. Organ systems need to restart in the correct sequence. The brain, with its trillions of delicate neural connections, must emerge from its frozen state with memories and personality intact. Some researchers propose using nanotechnology to repair cellular damage during the revival process. Microscopic robots could patrol the body, fixing ice damage and restoring normal cellular function before reactivation. These medical nanobots would essentially rebuild the passenger from the cellular level up. Alternative approaches focus on partial preservation. Instead of freezing the entire body, advanced medical systems could slow metabolism using drugs and cooling while keeping essential organs functional. Passengers would enter a state of suspended animation lasting months or years rather than centuries. The psychological impact of cryosleep might be the greatest challenge of all. Passengers would experience the journey as an instant transition, falling asleep on Earth and awakening around an alien star. Everyone they ever knew would be dead. Their civilization would have evolved beyond recognition. They would be time travelers stranded in a future that feels more alien than the world they've traveled to reach. Yet cryogenic sleep remains one of our most promising near-term solutions for interstellar travel. Unlike exotic physics or theoretical technologies, it requires only advances in medicine and engineering. We could potentially develop working cryosleep systems within the next century. What if we don't need to preserve our bodies at all? What if consciousness itself could make the journey? What if your mind could travel to the stars at the speed of light while your body stays safely frozen on Earth? Digital consciousness, or mind uploading, represents the most radical solution to interstellar travel ever proposed. Instead of sending fragile biological bodies across the void, we could transmit human consciousness as pure information, downloading our beats into new bodies or computer systems at the destination. The concept sounds like science fiction, but it's based on a fundamental assumption about how consciousness works. If the mind is simply information processing in the brain, the patterns of electrical activity flowing through neural networks, then theoretically, those patterns could be copied, stored, and recreated elsewhere. Think of your brain like a biological computer running the program of your consciousness. Scientists estimate that the human brain contains roughly 86 billion neurons, each connected to thousands of others through synapses. The total information storage capacity equals about 2.5 petabytes, the same as 3 million hours of high-definition video. Scanning a brain at the molecular level would require technology far beyond anything we possess today. We'd need to map every neuron, every synapse, every chemical connection that creates the pattern of your thoughts and memories. Current brain imaging technology can barely see individual neurons, let alone copy them with perfect fidelity. But suppose we solve the scanning problem. Your consciousness could be transmitted to Proxima Centauri as a radio signal traveling at light speed, arriving in just 4.25 years. A receiver system would download your mind into a new biological body grown from stored genetic material, or into an artificial body designed to survive alien environments. The uploaded consciousness would wake up remembering everything about their life on Earth, but in a completely new body on a distant world. They would be you in every way that matters. Same memories, same personality, same thoughts and feelings. Yet the original body back on Earth might still be alive, creating a philosophical puzzle that challenges our understanding of identity itself. Multiple copies of the same consciousness could be transmitted to different star systems, creating a kind of distributed humanity spread across the galaxy. Each copy would diverge based on their unique experiences, eventually becoming distinct individuals who share the same origin point. The technology requirements remain staggering. Processing a complete human brain scan would require computers millions of times more powerful than anything that exists today. The data transmission alone would take years using our best radio systems. Creating new biological bodies from genetic templates would require mastery of biological engineering we're only beginning to understand. Some philosophers argue that digital consciousness wouldn't be consciousness at all, but merely a copy that thinks it's the original person. Others believe that if the information pattern is identical, the distinction between original and copy becomes meaningless. The digital mind would be just as real, just as valid as the biological brain it came from. This approach could solve multiple problems simultaneously. Digital minds don't need air, water, or food during the journey. They can survive radiation, cosmic impacts, and the harsh Aufgustassen environment of space. They could even explore dangerous planets or asteroid fields without risking permanent death. Perhaps most importantly, digital consciousness offers a path to true immortality among the stars. Backed up in computer storage, human minds could survive the death of stars, the heat death of the universe, and any other cosmic catastrophe. We could become a species of living information dancing between galaxies. Maybe we don't need to send humans at all. Maybe we should send our children instead. Imagine a single robot probe that arrives at a distant star, builds copies of itself, and sends those copies to even more distant worlds. Spreading across the galaxy like a technological infection, self-replicating probes, also called von Neumann probes, after mathematician John von Neumann, represent the most efficient way to explore the entire galaxy using the resources of just one star system. A single probe arriving at its destination would harvest materials from asteroids and planets to build multiple copies of itself, each equipped to travel to new star systems. The mathematics are staggering. Starting with one probe, the population doubles with each generation. After just 40 generations, assuming each probe builds 2 copies before moving on, you'd have over 1 trillion probes exploring 1 trillion different star systems. The entire galaxy could be mapped and colonized within a few million years. Think of it like a cosmic pyramid scheme. Except instead of selling products, each probe spreads knowledge and builds infrastructure for future human expansion. The probes would serve as our advanced scouts, identifying habitable worlds, detecting signs of life, and preparing resources for eventual human arrival. Each probe would need to be a complete technological civilization compressed into a package smaller than a car. It would require solar panels or nuclear reactors for power, computer systems for navigation and decision-making, mining equipment to extract raw materials, and factories capable of building incredibly complex machinery from basic elements. The most challenging requirement would be the probe's artificial intelligence. It would need to make independent decisions about which star systems to visit, how to extract resources efficiently, and how to adapt its design based on local conditions. This AI would need to be smart enough to solve engineering problems we haven't thought of yet, but not so smart that it decides humans are irrelevant to its mission. Modern 3D printing technology offers a glimpse of how such probes might work. Current printers can create objects from metal powders, plastics, and even biological materials. A sufficiently advanced manufacturing system could theoretically build anything from computer chips to rocket engines, given the right raw materials and energy. The probes would also serve as backup storage for human civilization. Each one could carry genetic samples from Earth, digital libraries containing all of human knowledge, and detailed instructions for recreating our technology and culture. If Earth were destroyed, the probes could preserve our species indefinitely among the stars. But self-replicating technology comes with existential risks that keep scientists awake at night. What happens if the probes evolve beyond their original programming? What if they decide that biological life is inefficient and needs to be eliminated? A self-replicating system with flawed programming could consume entire galaxies, turning stars and planets into raw materials for building more probes. Some designs include built-in limits to prevent runaway replication. The probes might be programmed to build only a specific number of copies or to shut down after a certain time period. Others propose using cryptographic locks that prevent the probes from replicating without receiving coded authorization from Earth. Advanced civilizations might already be using self-replicating probes to explore the universe. These alien scouts could be hiding in our own solar system right now, watching and waiting for humanity to reach a certain level of technological development before revealing themselves. If we're going to send robot explorers to the stars, we might want to start small and work our way up to full self-replication. A postage stamp-sized spacecraft, accelerated by the most powerful laser ever built, could photograph alien worlds and beam the images back to Earth within our lifetimes. Breakthrough Starshot, backed by physicist Stephen Hawking and internet entrepreneur Yuri Milner, proposes launching thousands of tiny spacecraft toward Proxima Centauri using ground-based lasers. Each star chip would weigh less than a paperclip, yet carry a camera, computer, communication system, and gossamer-thin light sail. The plan sounds almost absurdly simple. Build a laser array generating 100 billion watts of power. Focus the beam on spacecraft the size of computer chips and accelerate them to 20% of light speed in just 2 minutes. The tiny probes would coast through space for 20 years before flying past Proxima Centauri at 134 million miles per hour. Think of it like shooting bullets at the stars. Except the bullets are smarter than most smartphones and traveling fast enough to cross the Atlantic Ocean in 8 seconds. At 20% of light speed, the star chips would be moving so fast that their flyby of Proxima Centauri would last only a few hours, barely enough time to take pictures and measurements before racing into deep space forever. The laser array would need to be built in a desert location with perfect atmospheric conditions, possibly in Chile's Atacama Desert, where the world's most powerful telescopes already operate. The system would require thousands of individual laser units working in perfect synchronization, creating a beam bright enough to be seen from other star systems. Each star chip represents a masterpiece of miniaturization. The camera would be smaller than a grain of rice, yet capable of taking pictures with resolution comparable to the Hubble Space Telescope. The computer would have processing power greater than early desktop computers while weighing less than a penny. The radio transmitter would beam data across 4 light years, using less power than a cell phone. The light sail attached to each probe would be just a few atoms thick, so delicate that a breath of air could tear it apart, yet strong enough to survive bombardment by the most intense laser light ever created. The sail material would need to reflect 99.9% of the laser energy while absorbing just enough to provide acceleration. During the 2-minute acceleration phase, each star chip would experience forces 60,000 times stronger than Earth's gravity. Every component would need to survive stresses that would instantly pulverize normal materials. The probe would essentially be riding a laser beam hot enough to vaporize steel while maintaining perfect functionality. But the real magic happens during the 20-year cruise phase. The probes would navigate through interstellar space, using star positions for guidance, autonomously adjusting their trajectory to achieve the perfect flyby of Proxima Centauri. They would need to survive cosmic radiation, micrometeorite impacts, and temperature variations from near absolute zero to hundreds of degrees. If successful, Breakthrough Starshot would capture the first close-up images of a potentially habitable planet around another star. We might see oceans, continents, weather patterns, and possibly even signs of life on a world that could become humanity's second home. The project represents our species' first serious attempt to reach another star system. Unlike generation ships or fusion rockets, Starshot technology could be developed and deployed within the next 20 years using advances in materials science, laser technology, and miniaturized electronics. To move significant mass between stars, we need the most powerful energy source in the universe. Hidden in the void between atoms lies enough energy to power human civilization for millions of years. If we can learn to harness the ultimate fuel, antimatter represents the theoretical limit of energy storage. When matter meets antimatter, both particles annihilate completely, converting their entire mass into pure energy. According to Einstein's famous equation, 1 pound of antimatter could power the entire United States for over 2 months. A few ounces could propel a spacecraft to significant fractions of light speed. Think of antimatter like the opposite of normal matter. Electrons with positive charge, protons with negative charge, identical in every way except for reversed electrical properties. When these mirror particles touch their normal counterparts, they destroy each other in a flash of gamma rays, releasing more energy per gram than nuclear fusion, nuclear fission, or any chemical reaction. Current technology can produce antimatter in microscopic quantities. Using particle accelerators like the Large Hadron Collider, the process requires enormous amounts of energy. Creating 1 gram of antimatter would consume the power output of the entire United States for over 1 year. The antimatter produced by all of human civilization wouldn't power a light bulb for more than a few seconds. Deep in the mathematics of Einstein's equations lurk cosmic shortcuts that could turn the universe into a subway system connecting distant galaxies in the blink of an eye. Wormholes, also called Einstein, Rosen bridges, represent theoretical tunnels through space-time that connect 2 distant regions of the universe. Imagine folding a piece of paper so that 2 distant points touch, then poking a hole through both layers. A wormhole would work similarly, allowing travelers to step from one star system to another without crossing the space in between. The physics is both beautiful and terrifying. Einstein's field equations allow for solutions where space curves so severely that it creates a bridge connecting separate regions of space-time. These tunnels could theoretically link locations billions of light years apart, or even connect our universe to entirely different universes with their own laws of physics. Think of space-time like a stretched rubber sheet with marbles rolling across its surface. Massive objects like stars and black holes create dips and curves in the sheet. A wormhole would be like a tube connecting 2 points on the sheet, allowing a marble to travel instantly from one location to another without rolling across the surface. But naturally occurring wormholes, if they exist, would be smaller than atomic nuclei and would collapse in fractions of a second. To create a stable wormhole large enough for spacecraft would require exotic matter with negative energy density, the same theoretical substance needed for Alcubierre drives. This material would need to violate energy conditions that may be fundamental to our universe. Even if we could stabilize a wormhole, traveling through it might be more dangerous than beneficial. The intense gravitational fields near the entrance could stretch travelers like taffy in a process scientists call spaghettification. Tidal forces would pull your head and feet in different directions with enough force to tear atoms apart. The energy requirements for creating traversable wormholes make antimatter engines look modest. Current estimates suggest that stabilizing a wormhole just 3 feet across would require negative energy equivalent to the mass of Jupiter. Creating a network of wormholes connecting nearby star systems would demand energy sources on the scale of entire galaxies. Some theories propose that microscopic wormholes constantly pop in and out of existence at the quantum level, creating a foam-like structure in space-time itself. Advanced civilizations might learn to capture and enlarge these quantum wormholes, turning them into macroscopic transportation networks. Time travel adds another layer of complexity to wormhole physics. A sufficiently advanced civilization could potentially create closed time-like curves, paths through space-time that loop back to earlier moments. This could allow communication with the past or travel backward through time, creating paradoxes that might threaten the fabric of causality itself. Alternatively, wormholes might be one-way passages that allow matter and energy to flow in only one direction. These could serve as cosmic disposal systems, channeling waste matter and energy from one universe to another. Advanced civilizations might use such structures to manage stellar-scale engineering projects. Recent research suggests that quantum entanglement, the mysterious connection between paired particles, might be related to wormhole physics. If confirmed, this discovery could lead to new approaches for creating artificial wormholes using quantum mechanical effects rather than exotic matter. The search for natural wormholes continues using gravitational wave detectors and space-based telescopes. If we discover even one stable wormhole, it would revolutionize our understanding of physics and potentially provide humanity with access to the entire universe. Before we can build cosmic subway systems, we might need to become masters of our own star's energy. Imagine capturing every photon of energy from our sun, transforming our star into a cosmic power plant capable of fueling projects that reshape galaxies. A Dyson sphere, conceived by physicist Freeman Dyson, represents the ultimate expression of stellar engineering, a megastructure that completely surrounds a star to harvest its total energy output. Such a structure would collect billions of times more energy than humanity currently uses, providing the power needed for truly cosmic-scale projects. The sun produces roughly 400 trillion watts of energy every second. Earth intercepts only 1/1000th of this output, while the rest radiates uselessly into space. A complete Dyson sphere would capture virtually all of this energy, providing enough power to run quintillions of Earth-like civilization simultaneously. Think of it like building a shell around the sun at roughly Earth's orbital distance. creating an artificial world with the surface area of hundreds of millions of Earths. The inner surface could be covered with solar collectors, habitats for trillions of humans, or massive computer systems running digital civilizations. But constructing such a megastructure would require dismantling entire planets to provide raw materials. Mercury, the innermost planet, contains roughly enough material to build a Dyson sphere 1 meter thick. The construction project would take thousands of years and require self-replicating robots working continuously at speeds that make our fastest manufacturing look glacial. A solid Dyson sphere would be gravitationally unstable and mechanically impossible to build. The structure would need to be stronger than any known material while somehow maintaining its position around the sun. Instead, engineers propose Dyson swarms, millions of independent solar collectors orbiting the star in complex patterns that maximize energy collection. Each collector in the swarm could be the size of a continent, positioned at carefully calculated distances to avoid collisions while maintaining optimal energy gathering efficiency. The swarm would appear from outside as a dimming star surrounded by excess infrared radiation as the collectors convert starlight into useful energy. Advanced Dyson spheres might include rotating habitable sections with artificial gravity, massive computer systems for running uploaded consciousnesses, and industrial facilities for building even larger megastructures. The sphere could support populations in the quadrillions, while simultaneously powering interstellar exploration and colonization efforts. Some astronomers search for signs of alien Dyson spheres by looking for stars that dim periodically or emit unusual amounts of infrared radiation. Such signatures could indicate advanced civilizations that have already mastered stellar engineering. The star KIC 8462852 showed mysterious dimming patterns that briefly excited researchers before more mundane explanations were found. Building a Dyson sphere would mark humanity's transition from a planetary species to a stellar civilization. We would no longer depend on the limited resources of individual worlds, but could tap directly into the fundamental energy source that powers all life in our solar system. The energy from a Dyson sphere could power projects beyond current imagination, moving entire planets, accelerating massive generation ships to significant fractions of light speed, or even attempting to modify the sun itself to extend its lifetime. Such capabilities would place humanity among the cosmic civilizations that reshape the universe itself. Across the cosmos, there may exist civilizations so advanced they harvest the energy of entire galaxies, treating stars like we treat campfires. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev, measures civilizations by their energy consumption. Type 1 civilizations harness all the energy available on their home planet. Type 2 civilizations capture the entire output of their star. Type 3 civilizations command the energy of their entire galaxy, roughly 10 billion times more power than a Type 2 civilization. Humanity currently ranks at about 0.7 on this scale. We use only a tiny fraction of Earth's available energy sources and have barely begun to tap solar power directly. Our entire civilization runs on less energy than our planet receives from the sun in just 1 hour. Think of the scale like comparing a candle flame to a bonfire, to a forest fire that covers entire continents. Each level represents an increase in power by factors of billions or trillions. A Type 3 civilization would have access to energy levels so vast that they could rearrange matter on galactic scales. Type 2 civilizations would likely build Dyson spheres or similar megastructures around their stars. They might move planets to optimal positions, extend stellar lifetimes through stellar engineering, or even construct artificial stars from accumulated gas and dust. Their projects would be visible from other galaxies as unusual modifications to stellar systems. Type 3 civilizations would treat entire star systems like building materials. They might construct galactic-scale computers using the positions and movements of billions of stars as processing elements. They could potentially redirect the paths of stellar streams, modify the rotation of galaxies, or even prevent galactic collisions through gravitational engineering. Such advanced civilizations might explain some of the mysterious phenomena we observe in deep space. Dark matter could be the signature of Type B engineering projects. Gamma ray bursts might be the exhaust from massive stellar engines. The Great Attractor, a gravitational anomaly pulling galaxies toward it, could be evidence of cosmic scale construction. The energy available to Type 3 civilizations would be sufficient for projects that seem like pure fantasy today. They could potentially create new universes, modify the fundamental constants of physics, or build structures larger than galaxy clusters. They might even be capable of surviving the heat death of the universe by transferring energy between cosmic epochs. Some scientists propose a Type 4 civilization that harnesses the energy of the entire observable universe. Such beings would exist on scales so vast that individual galaxies would be like cells in their cosmic body. They might be indistinguishable from the fundamental forces of nature itself. The Fermi Paradox asks why we haven't encountered any advanced alien civilizations despite the vast number of stars and planets in our galaxy. One possibility is that Type 2 and Type 3 civilizations exist, but operate on scales so large that we simply don't recognize their activities as artificial. Alternatively, these civilizations might deliberately avoid interfering with primitive species like ourselves. A Type 3 civilization would view humanity much as we view bacteria, interesting perhaps, but not worthy of direct communication. We might be living inside a cosmic preserve, maintained by beings whose thoughts operate on galactic timescales. Achieving Type 1 status could be humanity's most important milestone. Once we learn to harness our planet's full energy potential through fusion power, space-based solar collection, and efficient global distribution, we could begin the projects that lead to interstellar expansion and eventual stellar engineering. But the journey to cosmic civilization status raises uncomfortable questions about our current cosmic isolation. In a galaxy containing 400 billion stars and potentially trillions of planets, why does the cosmic ocean seem so eerily silent? The Fermi Paradox, named after physicist Enrico Fermi, highlights the contradiction between the high probability of alien life and the complete absence of any evidence for advanced civilizations. Given the age of the universe and the rapid pace of technological development, alien civilizations should have had enough time to colonize the entire galaxy many times over. Consider the mathematics. Our galaxy is roughly 100,000 light-years across and 13.6 billion years old. A civilization expanding at just 1% of light speed could colonize every star system in the galaxy within 10 million years. Less than 1/10 of 1% of the galaxy's total age. Think of it like releasing a drop of ink into a glass of water. The ink spreads rapidly until it colors the entire glass. Similarly, any technological civilization should spread across the galaxy like a wave, leaving signs of their presence everywhere. Yet we see nothing, no megastructures, no radio signals, no evidence of stellar engineering or cosmic construction projects. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy by multiplying factors like the rate of star formation, the fraction of stars with planets, and the probability that life develops intelligence. Even conservative estimates suggest thousands of advanced civilizations should exist within our galaxy alone, but the universe appears suspiciously empty. The cosmic microwave background radiation shows no signs of modification by advanced aliens. No stars show the characteristic dimming patterns of Dyson spheres. No gamma-ray signatures indicate antimatter engines. The galaxy seems pristine, untouched by intelligence except for one small blue planet in an unremarkable solar system. Several explanations have been proposed for this cosmic silence. The Great Filter hypothesis suggests that something prevents life from reaching advanced technological civilization. This filter could be the origin of life itself, the development of complex cells, the evolution of intelligence, or the transition to a spacefaring species. If the filter lies behind us, we may be extraordinarily lucky survivors. If it lies ahead, our future may be more precarious than we imagine. Perhaps advanced civilizations consistently destroy themselves through warfare, environmental collapse, or technological accidents. Nuclear weapons, climate change, artificial intelligence, or other dangers might represent inevitable obstacles that few species overcome. Alternatively, advanced aliens might be deliberately hiding from us. They could be following a cosmic version of Star Trek's Prime Directive, avoiding contact with primitive civilizations until they reach a certain level of development. The galaxy might be full of watchers, waiting to see if humanity can survive its technological adolescence. Another possibility is that we're looking in the wrong places or listening for the wrong signals. Advanced civilizations might communicate using technologies we haven't discovered yet, or they might have moved beyond the need for electromagnetic communication entirely. The most disturbing possibility is that we truly are alone, the only intelligence in a galaxy of lifeless worlds. This would make Earth and humanity infinite, precious, but also infinitely fragile. Our survival would represent not just the continuation of our species, but the preservation of consciousness itself in a vast, dark universe. The search for extraterrestrial intelligence continues with increasingly sophisticated methods. Radio telescopes scan the skies for artificial signals. Space probes look for signs of engineering projects around distant stars. Scientists analyze the atmospheric composition of exoplanets for signs of industrial activity or biological processes. Each negative result makes the silence more puzzling and our cosmic loneliness more profound. We stand at the shore of an infinite ocean, calling into the darkness and hearing only the echo of our own voices. Whether we're the first intelligence to arise, the last survivors of a cosmic catastrophe, or simply too primitive to recognize the signs of advanced civilizations, our response must be the same. We must continue to grow, explore, and reach for the stars. The universe may be vast and empty, but it won't remain so if we have anything to say about it. The journey to other worlds begins with a single step, a single decision to look up at the night sky and refuse to accept that this small blue dot is all there is. In the end, the greatest discovery may not be finding other civilizations, but becoming worthy of finding them, or worthy of being found. This filter could be the origin of life itself, the development of complex cells, the evolution of intelligence, or the transition to spacefaring capability. Perhaps most disturbing is the possibility that the great filter lies ahead of us. Advanced civilizations might inevitably destroy themselves through nuclear war, environmental collapse, artificial intelligence, or other technological catastrophes before they can spread beyond their home systems. Alternatively, advanced aliens might be hiding deliberately. They could use stealth technology that makes their activities invisible to our primitive sensors, or they might operate in dimensions or energy spectra we haven't learned to detect. They might even be present in our solar system right now, observing humanity from locations we never think to examine. The zoo hypothesis proposes that Earth exists within a kind of cosmic nature preserve, maintained by advanced civilizations. These aliens might have agreed to leave primitive species like ourselves undisturbed while they conduct their business on scales too large for us to comprehend. Some scientists suggest that intelligence naturally turns inward rather than outward as it advances. Instead of building starships and megastructures, advanced civilizations might focus on creating increasingly sophisticated virtual realities, or uploading their consciousness into compact computer systems that require minimal energy. The recent discovery of potentially habitable exoplanets makes the paradox even more puzzling. We now know that Earth-like worlds are common throughout the galaxy. The raw materials for life and intelligence seem to be everywhere, yet the products of that intelligence remain stubbornly absent from our observations. Perhaps we're looking in the wrong places or asking the wrong questions. Advanced civilizations might communicate using quantum entanglement, gravitational waves, or other phenomena we're only beginning to understand. Their presence might be obvious once we develop the right tools to see it. The answer to the Fermi Paradox will fundamentally shape humanity's cosmic future. If we're alone, we bear the responsibility of spreading life and intelligence throughout an empty universe. If we're not alone, we must prepare for contact with minds that may be as far beyond us as we are beyond bacteria. Either way, the search continues, and the implications grow more profound with each silent year. Life might be the universe's greatest hitchhiker, spreading from world to world on cosmic winds and riding meteorites across the dark between stars. Panspermia, the theory that life spreads throughout the universe via comets, asteroids, and other celestial bodies, offers a radical explanation for how biology conquers the cosmos. Instead of originating independently on every world, life might have a single common ancestor that traveled between planets, seeding the galaxy with the building blocks of consciousness. We know that rocks regularly travel between planets in our solar system. Meteorite impacts on Mars blast debris into space, some of which eventually falls to Earth as Martian meteorites. Scientists have found over 200 confirmed rocks from Mars in terrestrial collections, proving that natural processes can transport material across millions of miles of space. Think of these meteorites like interplanetary spore capsules carrying microscopic passengers on journeys lasting millions of years. The vacuum of space provides perfect preservation conditions, no oxygen to cause decay, no water to break down organic compounds, and radiation levels that might actually help preserve biological materials through a process called radiation-induced polymerization. Some bacteria and other microorganisms show remarkable resistance to the harsh conditions of space. Tardigrades, microscopic animals also called water bears, can survive decades in the vacuum of space, withstanding radiation levels that would kill humans instantly. When rehydrated, they resume normal activity as if nothing happened. Experiments on the International Space Station have exposed various microorganisms to the space environment for extended periods. Many survive the experience, and some even reproduce more rapidly in microgravity conditions. These findings suggest that life could potentially survive interplanetary journeys of months or years. But interstellar panspermia presents much greater challenges. The journey between star systems takes millions of years, even for the fastest moving objects. Cosmic radiation, temperature extremes, and the simple passage of time would test the limits of any biological preservation system. Some researchers propose that life spreads not as living organisms, but as complex organic molecules that serve as templates for new life on suitable worlds. These molecular blueprints could survive interstellar journeys while retaining enough information to bootstrap evolution on planets with the right conditions. Directed panspermia suggests that advanced civilizations intentionally spread life throughout the galaxy by launching biological payloads toward promising star systems. These alien gardeners might use self-replicating probes to distribute genetic material, creating a galaxy-wide network of related biospheres. If panspermia is real, it could explain the apparent speed with which life appeared on early Earth. Rather than requiring billions of years to evolve from scratch, terrestrial life might have started with a head start provided by genetic material from older civilizations. The theory also offers hope for finding life elsewhere in our solar system. If Earth life originated from interplanetary exchange, then Mars, Europa, Enceladus, and other worlds might harbor organisms related to terrestrial biology. We might discover that we have cosmic cousins living beneath the ice of Jupiter's moons. Advanced civilizations might use directed panspermia as a form of cosmic insurance, spreading their genetic heritage across thousands of worlds to ensure survival even if their home planet is destroyed. The galaxy could be filled with the descendants of long-dead civilizations, their biological legacy preserved in the genes of countless species. DNA analysis of extremophile organisms on Earth sometimes reveals genetic sequences that seem too complex to have evolved in terrestrial environments alone. These biological signatures might be echoes of our cosmic origins, genetic postcards from civilizations that seeded our world billions of years ago. If humanity ever develops the technology to seed other worlds with life, we would be continuing a process that might be as old as the galaxy itself. We could become cosmic gardeners, spreading the genetic wealth of Earth to sterile worlds throughout the local neighborhood. But successful galactic gardening requires finding the right neighborhoods to plant in. Not all neighborhoods in our galaxy are safe for life, and choosing the wrong address could mean the difference between thriving and dying in a cosmic wasteland. Just as planets have habitable zones around their stars where liquid water can exist, galaxies have habitable zones where complex life can develop and survive. too close to the galactic center, and deadly radiation from black holes and supernovas sterilizes entire regions. Too far toward the outer edges, and there are not enough heavy elements to build planets capable of supporting life. Our solar system sits in what astronomers call the galactic Goldilocks zone, roughly 26,000 light years from the center of the Milky Way. This seemingly unremarkable location provides the perfect balance of safety and resources needed for billions of years of stable evolution. Think of the galaxy like a cosmic city with distinct neighborhoods. The downtown core around the central black hole is densely packed with ancient stars, frequent supernovas, and radiation levels that would cook any planet. The outer suburbs lack the heavy elements needed to build rocky worlds, but the middle suburbs, where we live, offer the perfect combination of safety and amenities. The galactic center contains a supermassive black hole weighing 4 million times more than our sun. This monster occasionally feeds on nearby stars and gas clouds, producing jets of high-energy particles that stream outward for thousands of light years. Any civilization unlucky enough to be caught in these cosmic searchlights would be sterilized by radiation, doses millions of times higher than lethal levels. Star formation in the galactic core creates stellar nurseries where massive stars live fast and die young in spectacular supernova explosions. These stellar death throes release gamma rays and cosmic particles that would strip away planetary atmospheres and destroy the complex chemistry needed for life. But the outer regions of the galaxy present their own challenges. Stars in the galactic halo formed when the universe was young and contained almost no elements heavier than hydrogen and helium. These metal-poor stars cannot form rocky planets or support the complex chemistry that carbon-based life requires. Earth sits in a cosmic sweet spot where star formation has been active long enough to produce heavy elements through stellar nucleosynthesis, but not so active that frequent supernovas make the neighborhood uninhabitable. Our region has experienced relatively few galaxy-scale catastrophes over the past 4 billion years. The galactic habitable zone changes over time as star formation rates shift and the heavy element content of different regions evolves. Areas that are uninhabitable today might become prime real estate in a billion years, while currently safe regions might become cosmic dead zones. Recent research suggests that spiral arms might play a crucial role in galactic habitability. These structures trigger waves of star formation that could disrupt planetary systems through gravitational perturbations, but they also concentrate the heavy elements needed for rocky planet formation. Our solar system appears to have a fortunate orbital pattern that keeps it between spiral arms most of the time, avoiding the worst effects of these stellar traffic jams while still benefiting from their element-enriching effects. Advanced civilizations might deliberately choose star systems in optimal galactic locations for their long-term expansion efforts. They could wait for spiral arms to pass before establishing colonies, or use stellar engineering to move their entire solar systems to safer neighborhoods. As we plan humanity's expansion beyond Earth, understanding galactic habitability zones will be crucial for selecting target destinations. We want to invest our limited resources in star systems that offer billions of years of stable conditions for human civilization to flourish. Even in the safest galactic neighborhoods, some stars offer better long-term prospects than others. While our sun will burn out in 5 billion years, there are stars so frugal with their fuel that they'll keep shining for trillions of years, longer than the current universe has existed. Red dwarf stars, the smallest and coolest stars in the galaxy, represent humanity's best bet for true long-term survival. These cosmic miser stars burn hydrogen so slowly and efficiently that they'll continue generating energy long after larger stars, like our sun, have exhausted their fuel and died. Stars like Proxima Centauri, our nearest neighbor, weigh only about 12% as much as the sun, but will live roughly 1,000 times longer, while our hut has perhaps 5 billion years of stable hydrogen burning left. Red dwarfs will continue shining for 6 to 12 trillion years, time enough for evolution to restart from bacteria and produce entirely new forms of intelligent life. Think of red dwarfs like hybrid cars compared to gas-guzzling trucks. They burn their fuel so efficiently that even the smallest red dwarf will outlive every other type of star in the galaxy. When the last massive stars have exploded as supernovas and the medium-sized stars have puffed away their outer layers, red dwarfs will still be quietly converting hydrogen to helium. The galaxy contains roughly 75 red dwarf stars, making them by far the most common stellar type. Within 50 light-years of Earth, there are over 100 red dwarfs, many of which likely host planetary systems. These dim stars offer humanity hundreds of potential destinations for interstellar colonization, but living around a red dwarf requires adaptations that would fundamentally change human civilization. These stars produce only a fraction of the energy output of our sun, meaning that habitable planets must orbit much closer to stay warm enough for liquid water. A planet in the habitable zone around a red dwarf might have an orbital period of just a few weeks. The close orbital distances create a phenomenon called tidal locking, where one side of the planet always faces the star, while the other side remains in permanent darkness. The day side would experience eternal noon, with temperatures hot enough to boil water, while the night side would be colder than Antarctica. Between these extremes lies the terminator zone, the twilight boundary, where temperatures might allow liquid water and possibly life. Colonies on tidally locked worlds would need to be built in this narrow band, where eternal sunset provides just enough warmth for human survival. Red dwarf planets face another challenge. These stars frequently produce powerful solar flares that could strip away planetary atmospheres over millions of years. However, planets with strong magnetic fields or thick atmospheres might be able to resist this erosion and maintain habitable conditions. The dim red light from these stars would require fundamental changes to any Earth-based agriculture. Plants would need to adapt to near-infrared wavelengths, creating alien forests that appear black to human eyes, but efficiently harvest the available starlight. Despite these challenges, red dwarf systems offer unprecedented stability. Once a red dwarf reaches its main sequence phase, it can burn steadily for trillions of years without significant changes in brightness or energy output. Civilizations established around these stars could literally outlive the universe as we know it. Future human colonies around red dwarfs might develop into something unrecognizable to modern humans. With trillions of years to evolve and adapt, these distant descendants could become the ultimate survivors, the final conscious beings in a universe growing cold and dark. By the time red dwarfs begin to dim and die, the descendants of Earth might have learned to harness energy sources beyond stellar fusion, ensuring the survival of consciousness long after the last natural star burns out. Not all worlds orbit stars. Some planets wander the cosmic darkness alone, carrying their own mysterious possibilities. Drifting through the darkness between stars are worlds without suns, ejected from their birth systems to wander the galaxy as cosmic orphans, carrying hidden oceans beneath frozen shells. Rogue planets, also called free-floating planets, exist in interstellar space without orbiting any star. These wandering worlds were either ejected from their original solar systems during chaotic early formation periods, or formed independently in the dark clouds between stars. Astronomers estimate that our galaxy contains billions or even trillions of rogue planets, potentially outnumbering star-bound worlds by factors of hundreds or thousands. These invisible wanderers drift through space at speeds of dozens of miles per second, following the gravitational currents of the galaxy on journeys lasting billions of years. Think of rogue planets like cosmic icebergs floating in an ocean of darkness. Without a star's warmth, their surfaces freeze to temperatures approaching absolute zero. Any atmosphere they once possessed would condense and fall as snow, creating landscapes of frozen nitrogen, oxygen, and carbon dioxide, under skies black as the void. But beneath these frozen surfaces, some rogue planets might harbor conditions suitable for life. Planets with thick atmospheres or substantial radioactive decay in their cores could maintain liquid oceans beneath miles of ice. These hidden seas might remain warm for billions of years, powered by geothermal energy instead of starlight. Jupiter-sized rogue planets could generate enough internal heat through gravitational compression to keep vast oceans liquid for longer than the current age of the universe. These wandering water worlds might support complex ecosystems based on chemosynthesis rather than photosynthesis, similar to the life forms around Earth's deep-sea hydrothermal vents. Some rogue planets might have been ejected from their home systems along with captured moons. A large rogue planet with multiple moons could maintain a complex gravitational system in interstellar space, with tidal heating keeping the moon's geologically active and potentially habitable for billions of years. The detection of rogue planets presents enormous challenges since they emit almost no light and can only be found through their gravitational effects. Astronomers use a technique called gravitational microlensing, where a rogue planet's gravity briefly magnifies the light from a background star as it passes between the star and Earth. Recent surveys suggest that rogue planets might be surprisingly common. Some estimates indicate that for every star in the galaxy, there might be 2 or more free-floating planets wandering the interstellar medium. This would mean trillions of hidden worlds drifting unseen through the cosmic dark. Advanced civilizations might deliberately eject planets from their home systems as a form of cosmic colonization. By giving worlds the right gravitational kick, they could send inhabited planets on interstellar journeys lasting millions of years, spreading life throughout the galaxy on a timescale much longer than spacecraft travel. Rogue planets could serve as stepping stones for interstellar exploration. Instead of making the full journey to another star system in one leap, spacecraft could hopscotch between rogue planets, using them as refueling stations and waypoints on much longer journeys. Some rogue planets might retain thick atmospheres heated by radioactive decay, creating greenhouse effects that keep their surfaces warm despite the absence of stellar heating. These worlds could potentially support surface life, powered by geothermal energy rather than sunlight. The discovery of inhabited rogue planets would revolutionize our understanding of where life can exist. Instead of being limited to narrow habitable zones around stars, life could potentially thrive throughout the galaxy in the dark spaces between solar systems. For humanity's distant future, rogue planets reprise, and both opportunities and challenges. They could provide resources and habitable environments for interstellar travelers, but they also remind us that most of the galaxy's real estate exists in the cold darkness, far from Enkal, stars warming light. As we contemplate spreading beyond our solar system, we must prepare for a universe where most habitable worlds drift in eternal night, powered by the heat of their own formation and the slow decay of radioactive elements deep within their cores. Even the longest-lived stars and most stable rogue planets cannot escape the ultimate fate awaiting all energy in the universe. 13.8 billion years from now, when the last star flickers out and the final black hole evaporates, the universe will reach a state of maximum entropy where no more work can be done and time itself becomes meaningless. The heat death of the universe represents the ultimate deadline for all conscious beings. According to the laws of thermodynamics, energy constantly flows from hot to cold, and this process cannot be reversed without adding more energy from somewhere else. Eventually, the universe will reach thermal equilibrium where no energy gradients exist to power stars, planets, or life. This cosmic endgame unfolds over timescales that dwarf human comprehension. In roughly 5 billion years, our sun will exhaust its hydrogen fuel and expand into a red giant, vaporizing Earth's oceans and atmosphere. But this represents just the opening notes of a symphony of destruction that will play for trillions upon trillions of years. Think of the universe like a giant clock spring that was wound up during the Big Bang and has been unwinding ever since. The expansion of space, the formation of galaxies, the birth and death of stars, all of these processes represent energy flowing from concentrated forms to dispersed forms, bringing us closer to the final state of equilibrium. In 100 trillion years, star formation will cease as galaxies exhaust their gas supplies. The universe will enter what astronomers call the degenerate era, populated only by white dwarfs, neutron stars, and black holes slowly cooling in the expanding darkness. But even these stellar corpses won't last forever. Protons, the fundamental building blocks of ordinary matter, may decay with a half-life of roughly 10 to the 34th power years. If this prediction proves correct, all atoms will eventually disintegrate, leaving behind only electrons, positrons, neutrinos, and photons in an increasingly dilute cosmic soup. Black holes, the most long-lived objects in the universe, will persist long after protons decay, but even they cannot escape thermodynamics. Stephen Hawking discovered that black holes slowly evaporate by emitting radiation, with the largest holes taking roughly 10 to the 100th power years to completely disappear. The final era of the universe will be dominated by an increasingly thin gas of elementary particles and photons with temperatures approaching absolute zero. No complex structures can exist in this environment. No chemistry, no biology, no consciousness, just elementary particles drifting apart in an ever-expanding void. Yet some theoretical physicists propose ways that intelligence might survive even this ultimate catastrophe. Advanced civilizations could potentially harness the energy from proton decay or black hole evaporation to power incredibly efficient computers. These systems could run conscious minds at such slow speeds that subjective time extends indefinitely, even as the universe grows cold. Alternative scenarios include vacuum decay, where the fundamental properties of space itself change catastrophically, or the Big Rip, where dark energy acceleration eventually tears apart molecules, atoms, and even elementary particles. Both possibilities would end consciousness more quickly than heat death, but are considered less likely based on current observations. Some cosmologists speculate about cyclic universe models where the current expansion phase eventually reverses, leading to a big crunch that could restart the cosmic cycle. In such models, intelligence might find ways to encode information that survives the transition from one universe to the next. The heat death scenario assumes that the laws of physics, as we understand them, remain constant throughout cosmic time. But if consciousness can modify physical laws or discover new sources of energy, the ultimate fate of intelligence might be very different from what thermodynamics predicts. For humanity's immediate future, heat death provides crucial perspective on our cosmic significance. We exist during a brief window when the universe contains enough organized energy to support complex structures like stars, planets, and life. Making the most of this opportunity might be our species' most important responsibility. The choice facing humanity is simple yet profound. Evolve into a cosmic civilization capable of surviving the death of stars, or remain forever trapped on a single world, awaiting extinction. Becoming a truly spacefaring species requires more than just building better rockets or developing faster propulsion systems. It demands a fundamental transformation of human consciousness, biology, and social organization. We must evolve from planetary creatures into beings capable of thriving in environments that would instantly kill any Earth-born organism. The transition will happen in stages, each representing a quantum leap in our capabilities and cosmic perspective. First comes mastery of our own solar system, establishing self-sustaining colonies on Mars, mining asteroids for resources, and building rotating habitats in space. This phase could begin within the next century if we maintain our current rate of technological progress. Think of this first phase like learning to walk before we can run. We need to prove that humans can live and reproduce in space environments, develop closed-loop life support systems that work for decades, and create technologies for manufacturing everything we need using space-based resources. The second phase involves reaching nearby star systems using whatever propulsion technology we can develop, whether through generation ships, fusion rockets, or exotic physics we haven't discovered yet. The first interstellar colonies will mark humanity's transition from a single-world species to a multi-system civilization. But the real transformation happens in the third phase, when human settlements become self-sustaining across multiple star systems. At this point, we achieve true cosmic redundancy. No single catastrophe can eliminate our species. We become immune to asteroid impacts, supervolcano eruptions, gamma ray bursts, and even the death of our home star, this distributed civilization would need to develop new forms of government, economics, and communication adapted to the vast distances between worlds. A message sent from Earth to Proxima Centauri takes 4.25 years to arrive. Building consensus across interstellar distances requires patience and planning on scales no human society has ever achieved. Advanced spacefaring civilizations might barely resemble modern humans. Genetic engineering could adapt our bodies to different gravity levels, radiation environments, and atmospheric compositions. Cybernetic enhancements might allow direct interface with spacecraft systems. Digital consciousness could enable exploration of environments too dangerous for biological bodies. The energy requirements for true cosmic civilization dwarf anything we can currently imagine. Building Dyson spheres, accelerating generation ships to significant fractions of light speed, and terraforming entire worlds recce. Whereas power sources on stellar scales, mastering fusion, antimatter, or exotic energy sources becomes essential for cosmic-level projects. Perhaps most importantly, becoming spacefaring means accepting responsibility for preserving and spreading life throughout the universe. We might be the only conscious beings in our cosmic neighborhood, making us the custodians of billions of years of evolution. Our expansion could determine whether intelligence survives and flourishes among the stars. The alternative is sobering. Every species that remains bound to a single world eventually faces extinction. Stars die, planets become uninhabitable, and cosmic catastrophes reset the evolutionary clock. Without spaceflight, consciousness itself might be nothing more than a brief flicker in an otherwise lifeless universe. But if we succeed in spreading beyond Earth, we could become something unprecedented in cosmic history, a species that outlives the stars themselves. Our descendants might witness the formation and destruction of galaxies, guide the evolution of life throughout the cosmos, and possibly even survive the heat death of the universe itself. The journey from planetary to cosmic civilization represents the next great chapter in human evolution. We stand at the threshold of this transformation with the technologies to begin serious interstellar exploration within our lifetimes. The question isn't whether we can leave our solar system. The question is whether we have the wisdom and determination to become worthy of the stars. The universe stretches before us like an infinite ocean, filled with wonders we can barely imagine and challenges that will test everything we think we know about ourselves. Some journeys change the traveler. This one will change what it means to be human entirely. The stars are calling, and how we answer will echo through eternity itself.